All right, I hope you're sitting down because I have something very important to tell you about. It's the fundamental theorem of calculus part 2, and this is the very exciting part. When students think of the fundamental theorem of calculus, this is the part that they're thinking about. It says if f is continuous on the closed interval a to b, and capital F is any antiderivative of f on that closed interval a to b, then the definite integral from a to b of f of x dx is equal to capital F of b minus capital F of a. I cannot overstate how important this theorem is, because what this does is it finally gives us an easier way to evaluate definite integrals. This answers the question that we started thinking about way back in 5.1. We started by saying, okay, how do I find area under a curve? And we started with some approximations, and then we came up with this thing called the definite integral, and we said, well, that tells you the area, the net area, bounded by your curve in the x-axis, but we didn't have a way to evaluate it. Now we have a way to evaluate it. We are going to find an antiderivative and then plug in our upper limit of integration, plug in our lower limit of integration, and then subtract the two. So in order to understand where this comes from, we're going to say here, let f be any other antiderivative other than a. So here, remember a, we're going to use a of x to be that area function that we talked about in the last video. So the definite integral, let's say, from a to x of f of t dt. So this is what a looks like. So remember that antiderivatives, a function has infinitely many antiderivatives. And the thing that makes them different is the constant that you add, right? So you can add whatever constant that you want. So that means that capital F of x, which is an antiderivative of f, and we just wrapped up the last video here. We said, hey, let me erase this because this is so important. We said, hey, the area function is an antiderivative of f. So if a of x, this is an antiderivative of f of t. And we're saying f is some other antiderivative of f. So they're both antiderivatives, which mean for the most part they're going to look identical with the exception of this piece right here, that plus c. They might vary by a constant. It doesn't really matter what that constant is either. So notice that if I want to look at f of b minus f of a, so I'm taking this part, I'm actually starting over here on the right-hand side, f of b minus f of a. I'm going to use this relationship between f of x and a of x. So this is a of b plus c minus a of a plus c. A few things that we can say here. First of all, maybe we can distribute this negative sign. Well, c plus negative c, those two are going to cancel. So the constant that we added wasn't actually important. Didn't matter what it was. So I still have a of b minus a of little a. I got to figure out what is this guy. If I take that, I'm going to take this kind of up here off to the side. A of little a. Remember, a is this area function. Capital A, that's our area function. So this is the definite integral from a to a, f of t dt. And you tell me, well, hold on a second, Mr. H. Look at that. Your lower limit and your upper limit of integration are the same, which means that capital A of little a is equal to 0. So that means when I look at a of b minus a of a, that's a of b minus 0, or simply just a of b. So let's see if we can retrace our steps here. And actually here, I'm going to give, before I jump into this, let's say this, capital F of B minus capital F of A. This is equal to, we just showed that this piece is equal to A of B. So that's equal to capital A of B, which what is that? Remember, that's our area function right here, guys. This is so exciting. Look at this. This is the definite integral from A to B f of t dt. So this gives us a way to evaluate definite integrals. Doesn't matter what it looks like now. We don't need to look at the graph. We don't need to have a geometric shape. We can evaluate these definite integrals of many, many different functions now. It's not to say every function. Let's slow down there. But this says, you know what, if I want to evaluate the definite integral from a to b of f of t dt, that is capital F of b minus capital F of a, where f is just some antiderivative. This is so freaking cool. So we're going to practice using this fundamental theorem of calculus, because this is the part of the fundamental theorem of calculus that we're going to be using a lot going forward. We're going to see it a lot in this class. You're going to see it a lot in Calculus 2 if you plan on taking that. Calculus 3 as well if you plan on taking that. So here I want to evaluate these definite integrals using the FTC part 2. So here I have this definite integral from 0 to 2, 3x squared plus 2x dx. All right, so let's see. First I need to find capital F of x. What was capital F? Capital F is any antiderivative. Well, shoot, I can just use my power rule then. So capital F, so let's see if we can find our antiderivative. Antiderivative of 3x squared, that's going to be x cubed, plus antiderivative of 2x, that's going to be x squared. One thing I actually just forgot to mention, I'm going to add this in. Let me see where I have room to put this. I'm just going to write this up here. We'll come back to that example here in just a second. But when we write capital F of B minus capital F of A, the shorthand for this will say capital F of x evaluated at B and at A. So this is a notation that I'm going to be using a lot going forward. So all right, we have x cubed plus x squared. This was our antiderivative, and I'd like to evaluate this at 2 and at 0. So I have 2 to the third power plus 2 squared. So first I plug in my upper limit of integration. I will calculate this value, and then I will subtract. Now I'm going to plug in my lower limit of integration. 0 to the third plus 0 squared. So let's see, I have 8 plus 4 minus over here 0 plus 0. So I end up with 12 minus 0. My definite integral here has a value of 12. So that also means that if I wanted to look at the area bounded by 3x squared plus 2x over the interval 0 to 2, I can actually tell you what the net area is. It's 12. This is so cool, guys. I'm so excited. I'm so jazzed about this. All right, next up we got trigonometry, even better. The definite integral from 0 to pi over 4, I have 2 cosine of x dx. So first I need to find my antiderivative, of 2 cosine of x. So let's see, the antiderivative of cosine of x, that's going to be 2 sine of x. And again, remember, you can double check your work. Some of these antiderivatives, we haven't done them in a little bit here. If you're unsure, take the derivative of 2 sine of x. Do we get 2 cosine of x? Well, yep, we do. So I want to take 2 sine of x and evaluate it at pi over 4 and 0. So I'm going to look at 2 times sine of pi over 4 minus 2 times sine of 0. So 2 times sine of pi over 4, if I were to look at pi over 4, I should have radical 2 over 2 minus over here 2 times sine of 0. Sine of 0 is just 0. So the 2's cancel here. I've got radical 2 minus 0 gives me radical 2. One thing I will caution you of, you may look at these last two examples and say, hey, if my lower limit of integration is 0, I know that that second piece is just going to be 0, so I don't need to evaluate it. This is not always the case. Please be careful. You do need to take 0 and plug that value in. I'm hoping I have an example planned coming up here. I don't remember if we do, though. But just be aware, you do need to take this lower limit of integration and plug it in, yes, even if it is 0. Look at a few more here. So next up, I have the definite integral from -2 to +2. I have x squared minus 4 dx. So let's see. First, I need to find my antiderivative. So add 1 to the power, x to the 3, divide by my new power of 3. Minus here, I should have 4x, evaluated at -2 and +2. So let's see. This is going to look like 2 to the 3rd over 3 minus 4 times 2. Minus, I'm going to plug in my lower limit of integration now, -2 to the 3rd divided by 3 minus 4 times -2. So let's see, I've got 8 over 3 minus 8 minus over here -8 over 3, -4 times -2, I've got plus +8 here. Let's see, I don't really want to simplify each of these separately. Well, yeah, sure, let's do it. Let's see, I've got 8 over 3. If I want to think about 8, if I wanted to find a common denominator, this is really 8 over 1. 8 over 1, that's really the same as 24 divided by 3. So I'm going to take out this 8 over 1 and this 8, and we'll replace it with 24 over 3 and 24 over 3. So 8 over 3 minus 24 over 3, I should have -16 over 3. Minus over here, I should have a +16 over 3, which would give me a -32 over 3. So that is the value of my definite integral. Next up, let's see, what do we got next? We've got the definite integral from 9 to 4 of x minus square root of x divided by x squared dx. Here we need to do a little bit of rewriting. We need to be a little bit careful with this because the process of finding our actual antiderivative this time is a little bit tricky. So this is, let's see, the definite integral from 4 to 9. I'm going to do a couple things here. First thing I'm going to do is write this as x over x squared minus square root of x over x squared dx. The other thing I'm going to do, though, is square root of x, I know I'm going to have to rewrite that, so let me just do that now. I know that square root of x, that's really x to the 1/2 power. So I've taken this one fraction, I've broken it up into two separate fractions. I can simplify each of these fractions now. So definite integral of 4 to 9. Let's see, I've got 1 over x minus over here, I should have 1 over x to the 3/2 power dx. So okay, I need to do one more thing. I know what this guy is going to look like. The antiderivative of 1 over x, we know, well, of course, that's natural log. Antiderivative of this guy, though, maybe I'm not so sure. I should rewrite that with a negative exponent. So let me do that very quickly. 4 to 9. Got 1 over x minus x to the negative 3/2 dx. So now we're going to find our our antiderivative. So the antiderivative of 1 over x, it's natural log of absolute value of x. Antiderivative of x to the negative 3/2, we're going to have minus x. If I add 1 to the power, I should have negative 1 over 2. And then multiply by the reciprocal, so I'm going to multiply by negative 2 over 1. And I'd like to evaluate this at 9 and 4. And again, this is just kind of ugly to work with. I'm gonna clean this up a little bit here. Let's change that to a plus, and then also let's go ahead and say natural log absolute value of x plus 2 over square root of x, just because I think that's going to be easier to work with, evaluated at 9 and 4. So here, let's see, I will have natural log absolute value of 9. Now, since 9 is already positive, you don't necessarily need the absolute value there. You can just say natural log of 9 plus 2 over square root of 9 minus natural log of 4 plus 2 over square root of 4. So let's see, I've got natural log of 9 plus 2/3 minus natural log of 4 plus this will be 2 over 2, which is, I'm just going to simplify that to be 1 right away. So let's see, we're really subtracting these. I'm going to take this minus sign and distribute this through. So let's see, natural log of 9 minus natural log of 4. I could be really crafty and use a change of base formula. Or excuse me, not a change of base formula, a property of logarithms, say that's natural log of 9 over 4. I'm fine if we just leave it like this though. But then 2/3 plus negative 1, I should have minus 1/3 here. This is my exact answer. And then of course you could get a decimal approximation if you wanted to. All right, here, let's see. I've got 1/2 times the definite integral 0 to natural log of 2 e to the x dx. So this 1/2 really isn't going to play a big role here. It's just going to sit there on the outside. Let's see though. The antiderivative of e to the x dx. We said the antiderivative of e to the x is just e to the x. And we would say plus c, but since this is a definite integral, we no longer need our plus c. And we'd like to evaluate this at natural log of 2 and 0. So let's see, this is 1/2 e to the natural log of 2 power minus 1/2 e to the 0 power. So remember, e and natural log, these are inverse operations, so I'm left with 1/2 times 2 minus 1/2 e to the 0. E to the 0 power is, of course, 1. Anything finite to the 0 power is 1. So I have 1 minus 1/2 is 1/2 here. So notice the one thing I want to point out about this problem here, our lower limit of integration was 0. And when we plugged that in, when we looked at 1/2 e to the 0, we did not end up with 0. We ended up with 1/2. So make sure that you actually plug that value in. Like I was saying earlier, here is an instance where our lower limit of integration is 0. But when we plug in 0, we don't actually get 0. We got a different number. So you do have to plug that number in and check your work. I want to look at one last example before we wrap this video up. Example 4. Find the area of the region between the curve f of x equals x cubed minus 1, and I forgot to say, and the x-axis, on the interval -1 to 2. So the area of the region between the curve and the x-axis, this is a fancy way to say evaluate the definite integral of x cubed minus 1 dx from -1 to to positive 2. And that will tell me the area. In this case, they're just saying area, so I'm assuming we're talking about net area here. So, okay, we find our antiderivative. This would be x to the 4th divided by 4 minus x evaluated at 2 and negative 1. So let's see, I have 2 to the 4th divided by 4 minus 2. So this is my f of b minus f of a, negative 1 to the 4th over 4 minus negative 1. So we just have some numbers to crunch here. 2 to the 4th, let's see. That should be 16 over 4 minus 2. Minus over here, negative 1 to the 4th, that's going to be 1 over 4 plus 1. So let's see, 16 over 4, I've got 4 minus 2 here. Minus 1/4 plus 1, that should be 5/4. 4 minus 2, I've got 2 minus 5/4. 2, of course, that's the same as 8 over 4 minus 5 over 4 should give me 3 over 4. So this is really cool, guys. I really can't overstate how excited I am about this. When we're looking at this definite integral, when we have, let's do it in a different color here. When I'm looking at a definite integral from a to b of f of x dx, we really have a few steps. First, find the antiderivative or an antiderivative, antiderivative of f of x. So first you need to find that which we'll call capital F of x. That's our antiderivative. 2, we need to evaluate capital F of b minus capital F of a. So we're finding our antiderivative first. Once we have that, we're going to plug in our upper limit of integration, we're going to plug in our lower limit of integration, and subtract the 2. So this takes a process that we really had no idea how to start with, and gives us a very nice small set of instructions that we can evaluate now. Not any definite integral, but a lot more than we could before. So that seems like a good place to stop this video.